So let's talk about the Sagittarius A star we just took a photo of a few weeks ago. So the first black hole we ever took off is 2019. We took a black hole from the galaxy M87, Messenger 87. The black hole M87 star inside it. It is the first black hole was taken. A few weeks ago, we have taken our home star. Our galaxy's biggest black hole, Sagittarius A star. So we finally took a picture of it just a few weeks ago. So we have only took photos of 2 black holes. The Sagittarius A star was took for in the Event Horizon Telescope. It's a group of telescopes, and I will answer why. Okay. So actually, so this is normally how it works. Okay. So normally we use radio waves because radio waves has the lowest frequency, and they can travel very, very long distances. Because in reminder, Sagittarius A star is literally 30,000 light years away, which is, let me say, 300 quadrillion kilometers. I can't visualize it as much, but let's say here is Milky Way. Oh, so we are 1/3 of the Milky Way away from we're 1/3 of the Milky Way from here to Sagittarius A star. It is 1/3 of the length of the Milky Way galaxy. That's the only way I can visualize it. So yeah. It is extremely long away, how far away. But M87 it's like 2,000 times further away. But why did we take M87 first, then Sagittarius A, when M87 is so much farther? Well, because there are 2 reasons. Number 1, M87 is almost 2,000 times larger than Sagittarius A, which means that on a visual scale, it is only a tiny bit smaller than Sagittarius A. Number 2, M87 star is very active, not like Sagittarius A. Sagittarius A don't eat a lot of stuff, but M87 always eats stuff. So we can see its hot accretion disk more clearly. So yeah, so that's how we do it. So that's why M87 is actually, we first took it. So Sagittarius A star. Number 2, how did we take it? Okay, so we took it using Event Horizon Telescope. So imagine you have 2 satellites. Big telescope. Okay, if these 2 things observe the same place at the same distance, it's like, I can't very explain it. So because the Event Horizon Telescope is actually made out of multiple telescopes, and then they will produce a picture. Then if we stack it up with other pictures, we can see the picture of the Sagittarius A star. I am not good at explaining it, so maybe you should see the video yourself.
What's that?
You should see the video yourself. It's from one of my favorite YouTubers called Veterism. I think that's how he calls it. But I'm gonna explain it the best I can. So number 3, what are we actually looking at? Are we looking at, I don't know, the Event Horizon or the accretion disk? What? Well, it's neither. Because look. Oh this is how this guy is. This is a ball, which represents the black hole's event horizon. The event horizon is exactly one Schwarzschild radius, which is how we calculate the event horizon. It is exactly one Schwarzschild radius. So actually, if we put an equation this, actually, it doesn't exactly hit the event horizon. It is way beyond the event horizon, and at 3 Schwarzschild radii. That means if any matter falls below 3 Schwarzschild radii, then it will still get swallowed in the black hole. Because the reason why is because this matter is not fast enough, not like light. Light actually can orbit closer. It's called light can actually orbit 1.5 Schwarzschild radii. So it's called the photon sphere. But the photon sphere is unstable, so it might just shoot the light. Have two options. Normally it will be unstable, so it have only two options. One, fall into the black hole. Two, go out and go into infinity. So that's a photon
1
sphere.
kilometer, pace, 13 minutes, 44 seconds.
Okay, so actually, what we see is neither the photon sphere, the event horizon, or the disk, the accretion disk. Because if we shoot a light beam at it, if it hit the event horizon, it's gone forever. But because black holes actually warp space-time itself, light, instead of going straight, they go bendy. Well, actually, they don't go bendy. They still go straight, but black holes warp space-time, so that's why they go bendy. Understand? Mm-hmm. Good. So even if we send light to 1.5 Schwarzschild radii, it will still, because black holes warp space-time so much, it will still go into the black hole. Even 1.6, 1.7, 1.8, even 2 Schwarzschild radii, they will still go in. Even 2.5. So imagine if we send a light beam 2.6 Schwarzschild radii, then it will graze the photon sphere before heading out to infinity. So technically, what we're seeing is actually 2.6 Schwarzschild radii. Actually, we actually see the complete event horizon, because nothing, if you shoot anything at it 2.6 Schwarzschild radii, it will less than 2.6 Schwarzschild radii, it will gobble up and fall into the black hole. So that's what we're seeing. We're seeing the black hole at 2.6, the event horizon at 2.6 Schwarzschild radii. Because the light bends, so that's why even if they go just a little above the event horizon, still they will go in. Even they do double above the event horizon, they will still go in, because black holes warp space-time so much because they have so much gravity.